In this chapter, we're going to look at topics related to measurement. In this lesson, we're going to look at the surface area of pyramids and spheres. Hi everybody. So in this video here, we're going to take a look at the surface area of pyramids and spheres. Okay, so to start off with here, we're going to take a look at the characteristics of pyramids. Okay. A right pyramid is a three-dimensional object that has one base and an apex. Now that's the apex is going to be the vertex. Yoink! Got to show you the picture here. At the top of the pyramid here, and for a right pyramid, it's going to be directly above the center of the bottom base. Okay, so you might draw a little right angle, a little symbol right there, because it's going to go straight up to the vertex, and that's going to be the center of the base here. So the base is typically in the shape of a regular polygon, and the lateral faces are the shapes of triangles. Okay, so lateral meaning to the side. So you've got a base down here, and you've got your sides here. Okay, so prisms, like we see in the diagram here, prisms have, you got your two bases here, your top and your bottom, which we're going to call bases, both of them here. And then these larger rectangular sides here, those are your lateral faces. Here in a pyramid, the lateral faces are going to be triangles. Now, really important couple points here. It's very important to understand the difference between the pyramid height and the slant height. Okay, so the pyramid height is going to be the distance, if I can go back up to here, from the base all the way up to the apex there. So I mean, if you were looking at this pyramid and you wanted to see how high it was, I mean, you'd climb up to the top and you say, how high am I? That is different than the slant height, which is the length from the midpoint of the side here, the edge, along the triangular face up to the apex. Okay, that's the slant height. I mean, called the slant height because it's the one that's going to be leaning over there. So the line running up from the apex to the center, this is called the pyramid height, like I just said. It's 90 degrees to the base. And we use that to calculate volume. Okay, the actual height of the pyramid is going to be used to calculate the volume. The line running from the apex to the edge of the polygon is called the slant height, and we use that one for surface area calculations. Okay, and that's because it's going to be the height of the lateral. Probably says it's going to be the height of the triangular lateral sides here. Now, frequently, questions are going to give you the wrong dimension. So we're going to ask you for the surface area, but we're going to give you the height. Or we're going to ask you for the volume, and we're going to give you the slant height. So you can get the correct dimensions by using the Pythagorean theorem. An old friend. That Pythagorean theorem just shows up over and over and over again. Okay, so here we go. Just I give you another quick look at this. You got your slant height. Okay, for surface area, you've got the pyramid height used for volume, and then you've got the base edge and length of the triangle there. Anyway, now, additionally, our general formula for the surface area is going to look like this. Okay, because really what we're doing is we're focusing on the surface area now. We're going to take the area of the base, and then we're going to add up all of the lateral faces of the triangles around the pyramid here. So for the lateral faces, it's important to remember that these are triangles. They're not rectangles, they're triangles. Okay? And the slant height represents the height here. And remember, the area of a triangle will be 1/2 the base times the height. Now in this case, that base is going to be the length of the polygon on the bottom, and the height, this is going to be very specifically the slant height. Anyway, let's take a quick look at some examples here. All right, so in this problem, we're going to be asked for to look at the surface area of a square pyramid. Okay, and so the base is a square. The lateral faces are going to be 4 identical triangles, and I know they're identical because the base is a square, so all of the sides are going to be the same here. And we're still assuming that's a right pyramid. So in other words, that apex is right above the center. We're not tilting it off to one side or whatever. Now the easiest way to do this is to simply, if this was like a cardboard shape or whatever, slice along the edges of the triangle and then open it up to get the net. Okay, so here's the net here. So our surface area, okay, our surface area is going to be, first of all, the base area, which is the square at the bottom here. Each side is 9, so it's going to be 9 squared. Plus, now bear in mind, there are 4 lateral triangular sides here. So 4, that's what that's all about here. And then I've got this whole thing divided by 2. That's because it's a triangle. Okay, these are all triangles here. And the area of a triangle is half the base times the height. Now, the base here is going to be 9. And the height, well, in this case here, the height is given. The slant height is given. I'm not asking you for the volume of the pyramid. We're asking you for the area. So that's what we want, the slant height here. So that's going to be 11. And now let's just go to the calculator. We'll just enter that all in. So 9 squared plus 4 times. Now in the numerator, this is going to be 9 times 11. And then we're going to divide that by 2. And we get 279. What are our units here? Oh, no units given here. So we'll just use a little u squared. Units squared. Now, if it's a rectangular pyramid, what happens here is we've got 2 pairs of identical triangles. They're not all the same. And this is actually a really good diagram here because it really exaggerates the difference here so it's easier to see. So we've got the rectangular base. And then this triangle here and the triangle on the other side, those will be the same. And this kind of larger base triangle here will be the same as the one on the other side of the triangle, and those are the same. But these 2 triangles are not the same. The ones that are right next to each other aren't. So that's why our surface area formula takes that into account. So it's length times width for the base, and then we've got 2 identical triangles on 2 sides here and 2 identical triangles on the other side. Easiest way to see that, once again, is to tear this thing apart into its net. And so we just open this up here, open up the sides, and then fold out the triangles. So our surface area here will first of all be the area of the base, which we know is going to be 10 inches by 5 inches. So 10 inches, 5 inches. And then let's do the 2 smaller triangles here, the 2 narrower ones. So there's going to be 2 of those. I'm going to divide by 2 because it's going to be 1/2 the base times height. Well, the base is going to be 5. So 5 inches times, and we give you the slant height at 15.8 inches. I'll let the calculator handle that in just a second here. Now I'm going to add to that 2 times, and this time I'm going to focus on these 2 triangles here. And again, I'm going to have that divide by 2, that 1/2, because that's how you do that with triangles. The base in this case here is going to be 10. And then the slant height here is going to be 15.2 inches. And notice that those slant heights are different. Okay, not only are their bases different, but the slant heights are different. Once I've written that all up like this, now I can go to my calculator, and now we can just plug this all in. So 10 times 5, there's the base, plus 2 times 5 times 15.8, divide by 2, plus 2 times 10 times 15.2 divided by 2. And we get 281. And this time we already know what the units are, but I'm going to put inches here because it's easier to write that as inches squared when I use that notation. Let's take a look at another one. This time it's a triangular pyramid. Okay, well, so the base is going to be 1 triangle here. But it could be any sort of triangle, right? They could be a scalene triangle. It could be isosceles. It could be equilateral. I mean, I would really like it if it was equilateral because then all the lateral triangles will be the same. Okay, but they might not be. So this is for the lateral faces, triangles corresponding to the base triangle type here. So if it's equilateral, then we're going to have 3 identical triangles. That would be awesome. If it was isosceles, okay, well then we're going to get 2 identical triangles, and that's because with an isosceles base triangle, 2 of those sides are the same. But here, 3 unique triangles, this is going to be scalene. So it's hard to say. It's hard to say. You might need 1 triangle formula for the base, and then you might need 1 for each of the 3 sides, the lateral sides. I don't know. Maybe you can take a shortcut if you recognize the scenario here, but you might not be able to. So let's have a look at this particular example here. So what we've got here is this side is 10, this side is 14, this side is 14. Okay, so this is an isosceles triangle. The base is what I'm referring to here. The base is an isosceles triangle. Now, once again, in order for me to really see what's going on here, I'm going to open this up. I'm going to I'm going to use this idea of this net. Okay, I'm going to cut along the sides, open up the triangles here. Now, notice that these two triangles right here each have a base of 14 and a slant height of 12.4. This one is different. It's got a base of 10 and a slant height of 12.8. So my surface area is going to be, well, first of all, I'm going to have to figure out what the area of the base of that triangle is. This triangle right here. This 14 by 14 by 10. Ugh. Okay, so I got a little bit of work to do. I'm gonna drop this down over here because I'm gonna need, actually I'll put it up here. I'll do it up here. I need a little bit of work here. So what I've got here is I'm gonna drop an altitude on that triangle, and I know that the base is 10. But because it's an isosceles triangle, I know that that altitude is going to cut that base in half. So the base was 10. It's going to be 5 and 5. And then I know that each side is going to be 14. So what I'm going to do here is I'm going to use the Pythagorean theorem to figure out what the height is of that base triangle, because that's the one that I need information on. Well, that's going to be pretty easy to do, because height squared plus 5 squared will equal 14 squared. Okay? So I'm just going to pull out the calculator. I'm going to let it do the work, because remember, that's fine. So h squared plus 5 squared is going to be 25. And then what I suspect most people aren't comfortable with is that 14 squared, which is going to be 196. Okay, and then we're just going to subtract from there the 25, because we're going to bring that over to the other side here. And I'll get h squared is equal to 171. Now, for my last step here in this one, I'm going to take the square root of both sides. And I'm going to get the square root of 171, which is, okay, so it's approximately 13.1. But I'm going to leave that number on my calculator just for a moment here. Now, actually, in fact, I'm going to draw this little SA down just a wee bit lower so I have more room here. So now my surface area is going to be 1/2, okay, this is going to be the length times width of my base, plus 2 times 1/2 length times width. Now that's because of the two identical triangles here. But then I've got this one extra triangle here, which will be length times width divided by 2. Okay, this guy right here. So now, and normally I wouldn't use the same variables to refer to different triangles here. Okay, I might say this is like the base, this is the base, this is the first triangle, this is the second maybe triangle there. But in this particular case here, I know what I'm doing. As long as I'm careful going through this, I'm okay. But yeah, it's a little awkward using the same variables repeatedly, but that's okay for right now. So this will be 1/2. Okay, this will be the base here is going to be 10, and then the height there will be 13.1. But I'm going to use the number on my calculator. Then I'm going to get 2 times. Each of these triangles is going to be 14 times 12.4 over 2. And then finally I'm going to get 10 times 12.8, divided by 2. I'm almost at the end there. And now let's plug that into the calculator. So 1/2 multiplied by 10 multiplied by the answer that I just came up with, plus 2 times 14 times 12.4 divided by 2, plus 10 times 12.8 divided by 2. When I press equal, I'm going to get 302.98. Well, I'm going to round that to the nearest tenth here. So this is going to be approximately equal to 303.0. That 8 right there is going to cause the 9 to go up 1, which will cause me to add 1 to the 2 there, and then this will be a 0 there. And this will be, once again, inches squared. All right, now in this problem here, we're going to take a look at a more irregular shape from what we would normally do here. Now, it's still a regular polygonal pyramid, okay? Because the base here, now this is going to be a pentagon, but it's a regular pentagon, meaning that all the sides and interior angles are going to be the same. It's just when I say irregular before as an introduction, this is you aren't often going to work with that shape as a base. So maybe it's uncommon is probably a better word for it. Anyway, So what we're going to do here is each one of again, the lateral sides is going to be a triangle. They're going to be all identical because it's a regular polygon. So all the base sides will be the same. Now, one of the things I can do with a regular polygon here, particularly, specifically with this pentagon here is what I meant to say here. I can go from the center and draw lines to each one of the edges there, the sides of the pentagon. And that's going to create for me 5 equal triangles. Now, it doesn't really matter what the shape is. As long as it's a regular polygon, I can do that. And that's the significance of that 9.6 that was given to us in this problem. Okay, so when I've got this surface area length times width divided by 2 times the number of sides, that's what we're trying to do here. We're trying to figure out the area of the base. So this is going to be, for example, 1/2. Well, I know that each one of those bases is going to be 14. I mean, it was given to me in the problem here. And then I know that the height of each of these triangles is going to be this 9.6. So it's going to be 14 times 9.6. And then there will be 5 of them going all around that pentagon. Good. Now, I'm going to look at the lateral triangles. There are going to be 5 of those. And then for each one, I'm going to divide by 2. The length of the base there is going to be 14, just like it was for the triangles that are inside the pentagon. This time, though, I'm going to use the slant height, okay, for the height of each one of my triangles here. And this is given to be 19.5, so multiplied by 19.5. And again, this is just some calculator work here. So we've got 1 divided by 2 multiplied by 14 times 9.6. And then there are 5 of those triangles, plus 5 multiplied by 14 times 19.5, and then divide by 2, because that's needed in the area of a triangle. When I press enter, I'm going to get 1018.5. And I don't think units were specified here, so we'll just say U squared to indicate that it's an area. Okay, as we move through this here, the next one we're going to look at here is a cone. So we're going to start to use circles here. You're going to see we're going to end up with a sphere in just a moment here. So with a cone, the base is a circle, and then the lateral face, the side all around the cone, really forms this, what we call the sector of a circle. So a sector of a circle, if you got a circle right here, if you just take kind of a pie shape out of that, that's called a sector. Okay. Now, that sector can be quite large. Like in this case right here, you see it's quite large here. The formula is going to end up being pi r squared. Now, that's the area of the base. And then it's this one right here, pi times r times the slant height. Okay, so once again, with a cone, the slant height is significant. And you should see a parallel between the cone and the pyramid. Okay, you might think of the cone here as a pyramid with an infinite number of sides along the base here. And actually, that's not a bad way to think about it, because from there you actually can make a really nice connection to the formula of a pyramid and connect that to the formula for the surface area of a cone. But for the time being, just kind of take my word for it here. This is going to be pi times r times the slant height. So in this particular problem right here, the area of the base is going to be pi r squared. So pi multiplied by 14 squared. And really, one of the only things we can do to make this more difficult for you is give you the diameter, so that you have to divide that by 2 first to get the radius. And then we're going to add to that pi times, in this case, the radius is still talking about the radius of the base here, so 14. And now the slant height is this 45.2. Okay? So now we pull out our calculators. And when you're doing this, please use the pi button on the calculator. So for my Texas Instrument here, it's going to be second, and I'll press this button right here to get that pi button. And the reason being, when I do that, well, it's going to use this symbol right here, but the calculator stores in its memory enough decimal places that really rounding shouldn't cause any kind of an issue here. So pi times 14 squared plus pi times 14 times 45.2. And again, I'm going to round this to the nearest tenth, so it'll be 2,603.8. No units were given, so I'll say units squared. Okay, well, you might have been wondering, when's the sphere going to come up? Since the title of this lesson was about surface areas of pyramids and spheres. Well, here we go. At the very end here, we're just going to throw this in. The surface area of a sphere, the formula is actually really quite simple, but also really interesting that it works out the way it does. Spheres are unique in that they don't have bases or lateral faces. They just have this one continuous surface kind of all around the sphere here, the outside layer here. What's really interesting about this is if you were to cut this ball, let's say, in half, okay, it's going to expose a circular face. Okay, so it's like when you cut open an orange and you see that face with the fruit and the flesh of the fruit in it. Okay, it opens up this area here. Well, the surface area of the outside of the sphere is 4 pi r squared. The area of that circle that you expose when you cut it is just pi r squared. What's really interesting is that the surface area of the circle, the whole circle, is only 4 times that. Or I should say that it is exactly 4 times that. That's probably a better way to say that. It's really cool that turns out that way. So in this particular case here, for example, to come up with the surface area of the sphere, it's just 4 times pi times 4.5 squared. And notice we're using kilometers. That is one heck of a big square, circle there, I should say. So here we go. So it'll be 4 times pi, I'm going to use the one on my calculator, times 4.5 squared. And so, I'm going to round this to the nearest tenth. That's 254.5 kilometers squared for this particular problem. Okay, and there you go.